If you somehow stood on a neutron star's surface, you wouldn't just die instantly. You'd get flattened into a layer of atoms 1 millimeter thick before your brain could register what happened. A lot of people think neutron stars are just dense. They are. But dense doesn't capture what we're talking about. We're talking about a star that collapsed so hard it broke matter itself. People imagine neutron stars like heavy bowling balls, solid, heavy, but still normal stuff compressed down. That's not even close. A neutron star is what's left when a massive star explodes and its core gets crushed down to something smaller than a city but heavier than the sun. Everything that made it a star, hydrogen, fusion, light, gets stripped away. What remains is a ball of neutrons packed so tight the rules change. The surface is where things start getting weird. Gravity here is 200 billion times stronger than Earth's. That number sounds harmless until you picture what it does. If you dropped a marshmallow from 1 meter up, it would hit the ground at 7.2 million kilometers per hour. Not fall. Hit. Like a meteorite slamming into pavement. You wouldn't survive standing there. Your body would spread across the surface like paint. 1 millimeter thick. That's what 200 billion times gravity does to anything soft. The crust itself is made of iron. Normal enough, except it's not normal. The atoms are squeezed so tight they stack like bricks under unimaginable pressure. Mountains on a neutron star are only millimeters tall because gravity crushes everything flat. There's no room for peaks or valleys. The surface is smooth, hard, and completely unforgiving. Just below that iron crust, things get stranger. The nuclei start getting crushed into unusual shapes. Imagine squeezing a basketball so hard it turns into a pancake, then a rod, then a tube. That's what happens to iron nuclei under this kind of pressure. They can't stay round. They stretch, flatten, twist into shapes physicists call nuclear pasta. Spaghetti, lasagna, gnocchi. The names sound silly, but the structures are real. Long strands, flat sheets, clustered tubes. This layer is the strongest material in the universe. Stronger than diamond by a factor of 10 billion. And that's just the surface. We haven't even gotten to where the rules start breaking. The crust is weird. What's underneath makes the crust look normal. Once you pass the crust, you hit the inner layer, where neutrons start dripping out of nuclei, like water leaking from a sponge. Except it's not leaking. It's worse. Imagine squeezing a wet towel so hard the water doesn't drip. It phases through the fabric itself. That's what happens here. The pressure is so extreme that neutrons can't stay locked inside their nuclei anymore. They slip out and start flowing between the crushed iron atoms like a fluid moving through cracks. The weird part is the matter acts like liquid and solid at the same time. The nuclei stay somewhat structured, but the neutrons flow freely around them. The temperature here is about 1 million degrees. That sounds like it should matter. It doesn't. Gravity dominates everything. Heat is just background noise compared to the crushing weight pressing down from above. Go deeper, and you leave the crust entirely. Now, you're in the outer core. This is where we enter pure neutron fluid. Not water, not any liquid you've ever seen. A superfluid. That means it flows with zero friction. Imagine water that never stops moving once you stir it. Spin it once, it spins forever. No drag, no resistance, no slowing down. The superfluid doesn't just sit there either. It forms vortices, whirlpools that are perfectly straight lines. If you could see inside, you'd see millions of these vortex threads spinning in parallel like an impossibly organized tornado farm. They never bend. They never merge. They just spin. The fluid itself is so dense, a teaspoon would weigh 10 million tons. 1 teaspoon, the weight of 1,500 Great Pyramids. But it gets stranger. Protons start appearing in this layer, also in superfluid form. They flow just like the neutrons, but with one difference. They form a superconductor. Electricity flows through them with zero resistance. And because moving charges create magnetic fields, this generates a field a trillion times stronger than Earth's, strong enough to erase every credit card on the planet from halfway to the moon, strong enough to rip iron out of your blood if you got close. So far, we're still in territory where our physics works. We can test these states in labs, at least partially. Scientists have created superfluids and superconductors here on Earth. Tiny amounts, controlled conditions, but we know the behavior. We trust the models, but keep going down, and the equations start returning question marks. Now we're getting into the extreme. The next layer breaks the rules we thought were unbreakable. At the inner core boundary, density reaches nuclear density. That's the same density as inside an atomic nucleus. We've gone from a star-sized object to recreating the conditions inside a single atom, but sustained across kilometers. If you took all of humanity, 8 billion people, and compressed us to this density, we'd fit inside a grain of sand. The entire species. 1 grain. What exists here is controversial. Physicists have competing models, and none of them can be tested directly. We can't recreate these pressures on Earth. Our best particle colliders only reach these conditions for microseconds in spaces smaller than atoms. Here, it's sustained, permanent, and we're trying to understand it from 400 light years away. The problem is that neutrons might not be able to stay intact anymore. Quarks, the building blocks of neutrons, might not be able to stay confined. They could break free. If they do, you get quark matter. Neutrons dissolve into a soup of quarks, flowing freely like a liquid made of subatomic particles that normally can't exist on their own. It's like crushing ice so hard it stops being water molecules and becomes pure hydrogen and oxygen plasma. The structure breaks, the pieces scatter, but they're still bound together by pressure. Another possibility is hyperons. These are particles where strange quarks replace normal quarks. They don't exist anywhere else in the universe as far as we know. You can create them in colliders for fractions of a second, but here they might be stable. Permanent residents of the core. Exotic matter that only forms when you crush neutrons past their breaking point. Or it could be something else entirely. Something we've never seen in any lab or theory. Some physicists think the core might be a quark-gluon soup, the same state that existed microseconds after the Big Bang. Others think strange matter might be stable here. Matter so tightly bound, it could theoretically exist outside the star if you pulled it out. It would explode, but the physics says it might hold together for a moment. The fundamental question is whether we're still dealing with matter, or if we've created a new state that doesn't have a name yet. This isn't a star anymore in any normal sense. It's a laboratory testing physics at pressures nothing else in the universe can produce. Well, almost nothing. Add a bit more mass and the whole thing collapses. But we're not there yet. We're not done. Because there's one more question nobody can answer. At the very center, we don't know what's there. Gravity and density reach values where general relativity and quantum mechanics give different answers. They're both our best theories. They've both been tested thousands of times. But here, they disagree. One says the pressure does this. The other says it does that. And we can't run the experiment to find out who's right. The core might be quark soup. It might be a color superconductor, a state where quarks pair up and flow without resistance, like the superconducting protons in the outer layers. Or it might be something that requires new physics. Something we haven't thought of yet, because we've never needed to. We're trying to understand the rules of a game by watching through frosted glass. We see shapes, we see movement, but the details are blurred. Some models say there could be a tiny black hole forming at the center, not growing, not consuming the star, just sitting there, a microscopic point of collapsed spacetime at the heart of a neutron star. Other models say that's impossible. The pressure would prevent it. Or maybe the rotation would tear it apart before it could stabilize. Nobody knows for sure. What we do know is there's a limit. Add any more mass to a neutron star and it collapses into a black hole. The maximum mass is about 2 to 3 times the sun's mass. We've found neutron stars at 2.1 solar masses. That's close. Very close. If you added one more sugar cube's worth of matter to those stars, they'd tip over the edge. The transition from neutron star to black hole happens in milliseconds. The core can't hold. The pressure can't fight back, and everything falls inward past the point of no return. So let's put this in perspective. We've descended from a surface with 200 billion times Earth's gravity into a core where a teaspoon weighs as much as a mountain range, where the temperature is 1 billion degrees, where the density is the same as compressing the entire human race into a grain of sand, where the physics we use to describe everything else in the universe stops giving clear answers. That's not a star anymore. It's a wound in space-time that hasn't quite closed. It's matter pushed so far it forgot how to be matter. And it's balanced on a knife edge. One side is a neutron star, the other side is a black hole, and the difference between them is 1 sugar cube. So what does this tell us? What's inside a neutron star isn't really an answer. It's a question written in physics. We know the outer layers. We can test those in labs. We understand superfluids and superconductors and nuclear pasta because we can create smaller versions of those states here on Earth. But the deeper you go, the more you're forced to admit we're guessing. Educated guesses based on equations that work everywhere else, but guesses nonetheless. That doesn't stop us from trying. We've built telescopes that measure gravitational waves from colliding neutron stars. We've timed radio pulses from spinning neutron stars with precision that would make an atomic clock jealous. Every measurement gives us one more constraint, one more clue about what's happening in that core. And slowly, over decades, we narrow down the possibilities. Maybe in our lifetime, we'll know if quark matter exists at the center. Maybe we'll discover something stranger. The next time you hear about a neutron star, remember it's not just a dense object floating in space. It's a laboratory testing the absolute limits of physics. It's matter pushed so far, it forgets how to be matter. It's a place where our best equations shrug and say maybe. And somehow, from billions of light years away, we can study it. We can listen to it spin. We can watch it collide with others. We can measure the ripples it sends through space-time itself. A neutron star is only 20 kilometers across. You could drive past one in 15 minutes if it were sitting on a highway. But inside that city-sized sphere is a density gradient that takes you from normal physics to the edge of the unknown. From iron crust to quark soup. From equations we trust to questions we can't answer. And all of it held together by gravity so strong it bends light, time, and matter into something we're still trying to understand. We split atoms and thought we understood matter. We didn't. We built particle colliders and thought we found the bottom. We hadn't. Neutron stars remind us there's always another layer, always another extreme we haven't reached, always another place where the universe does something we didn't think was possible. And the fact that we can look up, spot these things across impossible distances, and slowly piece together what's inside them says something about us, too. We're stubborn. We're curious. And we don't stop asking questions just because the answers are hard. That's not just a star. That's physics breaking in slow motion.